Hello guys, welcome back to the Transformer Slam series. It's been quite a while since I last uploaded a video, and all this while I've been doing some other work, but at the same time I have also been learning more about vision transformers. So in this episode, we'll be talking about vision transformers, which which was the next thing according to the plan anyway. I must remind you all again, that this plan was made with the help of ChatGPT. So the plan that we have in this, it suggested to learn vision transformers using this particular GitHub repo. It's actually a very good repo, has a lot of different varieties of vision transformer, and it gives a very easy kind of interface to implement those vision transformers and its varieties. But while exploring more about it and learning more about it, I realized that there should be a better way to learn about this. And what I'm going to do is I'm going to go in a little bit of depth of transformers, what transformers are, what vision transformers are, and how things inside a vision transformer works. So I'll be getting into the nuances of it. So okay, let's start. Um, so there is a Medium article, uh, this particular one by Rishabh Singh, uh, which I believe is gives a very good explanation, a practical and a theoretical explanation of how vision transformers work. So I'll try to follow this, and we have the codes also here. We'll try to run this code. I'll try to also relate and explain this code based on whatever we have seen so far. So in previous videos we saw about creating neural networks, creating convolution neural networks. So some of the basic structure of creating model, creating data sets, all that remains the same. So I hope there won't be much of a problem to follow along. Okay, so let's start. Here what you see is the basic architecture of a vision transformer. In this area where you see the image that has been cut, or in proper terms you would say patchified, into many different sub images, and all of these images maintain their uh, order. Like for example, this first one here is the first one here. Let's zoom in a little bit. So the first image here is the first image here, second image here is the second here, third here is the third here, fourth here is the fourth here. So this order actually matters, and why we will be seeing later. But we need to remember that, when we patchify the image, we also need to maintain the proper order when we are creating the input tensor for that. Okay, so moving ahead, I will try to explain how the patchifying works. But before that, uh, let me draw some um let me draw out the architectures and some of these diagrams, because it's going to be helpful for us to understand more in future. Okay, so what I will do is I'll go over to my tab screen. I hope my screen is visible. We are uh, back after drawing all the diagrams. So I have all the diagrams here, and then I'll be explaining in detail what these are and how these work. Okay, so when we see here, we see that the first process that we have to do is patchify. Now let me explain how patches work. So suppose um, suppose you have an image, of 9 cross 9 pixel size. So we have 9 cross 9 pixel size. Uh, and you had to, you know, make parts of this image such that all parts are equal, right? So how would you make the patches, right? So normally what would happen is one patch you would make of 3 cross 3 size, same another patch 3 cross 3 size, another patch 3 cross 3 size, and that's what we have here representing these patches of 3 cross 3 size. Okay, so the thing is that in this particular example where we had a 9 cross 9 image, we got 9 patches of 3 cross 3 size each. But the thing is that normally image can be some other size, like uh, maybe 256 cross 256, and the number of patches that you create and the number of pixels in each patches, that can actually differ, right? So the total number of patches you create may be n, and the total, and for each patch the pixel might be of size p, right? But we have what we have to keep in mind is that this what we have to keep in mind is that this n is, I mean, this 2256, the size of the image is equally divisible by n. Okay, so that we have to keep in mind. And also same here, this n is divisible by I mean, sorry, this 256 is divisible by the number of n patches that we are making. So basically what we will have is p cross n will be 256. Okay, so I hope this was clear. Now, in this case, the shape and size of the tensor, how it will look like is, so since we have 3 cross 3 patches, right, and we have total of 9 patches, each of this patch, each of these, each of these, this patch will be flattened out into a single vector. So what we will be getting is, for each of them, what we will get is a vector with length 9, where each of these will be representing one particular pixel here, this, right? So how it will look like is 9 columns, 1 2 3 4 5 6 7 8 9 columns, where each of the column represents a patch. Okay, and for each of column, the length and size of each of the column will be 9, 1 2 3 4 5 6 7 8 9. Okay, here also it will be same, right? And each of this is representing a pixel, right? So that's how this particular column is going to represent a patch. Okay, so in this case, what does the shape and size become like? It becomes 9 cross 9. So 9 cross 9 is the shape of our input, very basic input tensor. Now, for the sake of this example, let's assume that we are not working with a 9 cross 9 image. For the sake of this example, let's just assume that the image that we have is of size 28 cross 28. In this case, and suppose if we are making patches of 7 cross 7, so that means we are creating 7 patches here, so 7 cross 7, and each of the patch is of size 4 cross 4. Okay, so this becomes the representation of 4 into 7 is equal to 28, and same here. Okay, so what we get is the shape of our tensor will be, the very initial shape of our tensor will be 7 cross 7 here and 4 cross 4 here, which is equal to 49 and 16, and this n here just represents the batch size. So suppose you have 10 images in a batch, so this n will be 10. Let's keep that in mind. Okay, so in this case the shape of or how the tensor would look like will be something like this, of 49 columns, and this here 16 rows, right? 16 rows and 49 columns. Then in this case again, as we discussed earlier, each of the column will represent a single patch. Okay, so like first column representing first patch, second column representing second patch, and so on. Okay, so that's how our input tensor will be formed. I hope this is clear. Now what we understand is this particular step, how our patches are forming the input tensor, so that we can do some layer operations on it, right? Pass it through layers and then pass it to our neural network. We'll see about that, but that was about it. So what we learned so far now is this part, how our image is converted into patches and how that patch forms the input tensor. Okay, now what happens after this? Seeing this diagram of ours, of the VIT, so this is the complete architecture diagram, right? So right now we are at this step. After that, what happens is a linear encoding layer. Okay, so in that what happens is uh, we will see here. Sorry for the bad handwriting. So what we have right now is, in this example as we discussed, we have 49 cross 16 size of tensor, and we remember this was 7 cross 7 and this was 4 cross 4, right? So we have our 49 cross 16 size of tensor. Now this goes through a linear transformation to do feature reduction, right? So in this case the 16 that we have here is basically the feature, right? So each of this is like a feature vector, right? So to reduce computation, what we do is we pass it through a linear transformation layer, which is basically like an nn dot linear. So nn here is like neural network. So nn dot linear is actually a very common method used for uh, linear transformation in PyTorch, right? So it passes through a linear layer using nn dot linear, where this becomes a 49 cross 8. Okay, so instead of having 16 features, these 16 features are boiled down into 8 features. So it's not that uh, it's it's not that each of this 16 is, it's not that only some part of it is removed and the rest of it remains. It's not like that. This 8 will have the complete understanding of all of this 16 because it is passing through a linear layer. So basically, in terms of like seeing in terms of neural network, suppose this you have a layer, and here you have 16 input nodes. Suppose this is 16, and here you have 8 input nodes. So we know that when it passes through a linear layer, the output will have all the information of input, just that it will be in the dimension, in the number of dimension defined. So in our case it will be 8, right? So I hope this is understandable. So it passes through the linear layer, and the features number of features are reduced, but still it encompasses all the features, right? So that's what happens in this linear encoding layer. Now we add a class token. So this CT here is representation of a class token, and then we add positional embedding. Okay, so what is a class token? So a class token is like a vector of same size that is added to the front of our tensor. Okay, so this will be of also 8 size. Okay, 8. So then our complete patch tensor becomes of what shape? It basically becomes 50 cross 8. Okay, along with our class token. Now what this class token does is, at first it is initialized with all the random values, but as we progress further, right, there is a lot of embedding that happens, as you can see here, positional embedding happening, and then the transformer encoding happening. So as we progress further, all of the operation that we do on the tensor happens on this class token as well. So what happens at the end is, because this class token goes through all the operation that this part of the tensor has also gone through, this becomes a small representation of this whole patch of image. Okay, or this, in this case, this whole tensor, right? So this single class token becomes the representation of this whole patch, and that's why it is important. And why it is called the class? Because when this will become a representation of this, you just need to classify this to understand which class this whole patch belongs to. Okay, so I hope this is understandable. Now we will be seeing about this positional embedding that is added to our tensor. So so far what we have seen is, we are at this point, right? We are at this point. At this point, our class token is not added, and at this point our tensor has gone through the linear encoding. The feature numbers has reduced. Now we add a positional embedding to it. We will see what that is. So this class token, what I explained earlier, please understand that this class token will be added to this whole thing before it goes to the transformer encoder. We'll see that, but let's understand how positional embeddings are added. So far what we have is, our tensor got reduced to size 49 cross 8. When it goes through positional embedding, embedding is a function of sine and cos, which generates the values such that it comes out in a pattern. Okay, and why that is important is, suppose it comes out in a pattern, we will see how what those patterns are shortly. Actually, let me just go ahead and show you. So this is a sample code that creates positional embedding and also visualizes it. Okay, so you see here, so these are our columns, okay, and these are our rows. So in this example, the column size is, I think, around 300, and the row size is around 100. Okay, yeah, see this 300 and 100. Okay, so this kind of pattern is generated. What happens is, in if you see one particular uh, row in this, okay, one particular row, okay, none of the particular row will have the same value as any other row. Okay, so when we add this, when we generate this kind of positional embedding and we add it to our, all these values gets added, okay, to the values like this. Okay, so what that does is that it influences the value of this tensor and each of its rows to also change in such a way that no two row value remains the same. Okay, but at the same time, because we know that, what is our function that has generated these positional embeddings, so this is the function. Because of that, we are able to understand, so given any row and any pixel values inside it, right? So in this case it will be like feature values. So uh, any of those two feature values will know that if given this, what is the relative position of this to this. Why? Because they are interrelated with to each other by this function that we have here. Okay, and at the same time, each of the rows are also unique in itself. Okay, so why that is important and how it works out later we will see, but that's what the positional embedding is about. Okay, and now that we have our positional embedding, okay, so basically this positional embedding and adding it to the tensor is done. Going back to the class token, the class token is added after the positional embedding step. I am sorry that I explained it earlier, but class token is added after the positional embedding step, so that it's already, all of it is already unique. So the class token will be a unique representation. Okay, so here our class token is also added, and then it is sent to the transformer encoder block. Now in next episode we will be seeing what these transformer encoders do, okay, and how do they work. Okay, so here we have the architecture of the transformer encoder block. Okay, and this is where the multi-headed self-attention happens, and this is the architecture of multi-headed self-attention, and we'll also be seeing in detail how this works. Okay, so we'll get into the transformer encoder block and the uh, nuances of how it works in the next video.